Good morning. So we were today on our seventh lecture of our course, Vehicle Dynamics. Of course, we are learning in first module fundamentals of mechanical vibration. And in the last class, we just have done damped free vibration. So we started our class understanding what is this damping all about. So damping is another important element that is the constitutive of vibratory system. At first hand, we learned simple harmonic motion, which is the base for your fundamentals of mechanical vibration, without considering this damping aspect. So our system was only conservative system. There is no resistance for our vibration motion. And we were able to derive the governing equation applying Newton's second law. And then we were able to find the response of the system, and the arbitrary constants that were present in the response were found out by applying initial conditions. So any vibration that's executed by itself without any external agency, external force, is what is called the free vibration, and that can be in a system as possible with an initial disturbance by giving an initial push of the motion. After that, there is no external force, and that it vibrates on its own and continues, and that's what is called the free vibration. And that is essentially possible when you do not have damping present in the system. If you have damping present in the system, though you call a free vibration, that cannot continue for a long. It will stop at a point of time, because the damping is taking a form of resistance for the vibratory system. And that's where we have understood the damping can be of three types: viscous damping, dry or Coulomb damping, or material hysteresis damping. And commonly used damping is viscous damping in vibratory system, especially in automotive application. If you look at, we have mostly, especially on suspension, we see that dampers are modeled by viscous damping. Unless you have to model your tire, where the tire is viscoelastic material, and there you require this hysteresis type of damping, where it can also be equivalently represented by means of spring and damper viscous damping system. And there are constitutive models for that to do so. So this is all something in background. We are very much aware about damping. And the important nature of the damping is, unlike the spring, it cannot store the energy. It would only dissipate the energy. So the energy dissipation in vibratory system is all because of the damping nature of the system, or damping present in the system. So today's class, we are going to continue with what we have learned in damped free vibration, that essentially its governing equations, trial response, and the trial response can take in another form also that you have seen, and then a determination of arbitrary constants. That is similar procedure that whatever that we have followed in natural free vibration. So this is what we have essentially seen in the last class, its response and its governing equation. I'm going to continue today from that point. I'm going to add some of the important properties of this damping in the system. So for that, let me just share my screen. Quickly, let us look at the point where we stopped in the last class. Is this? So we were looking at the underdamped system, where we had the two roots of the characteristic polynomial given by S1 and S2, and our response was represented by this, and you can essentially represent, these are the three different forms of your response of under-damped free vibration. And we just concluded looking at the relationship between omega d and omega n, or omega d by omega n ratio to zeta. So here we were learned that omega d is what is called a damped natural frequency, omega n is what is called natural frequency, and zeta is what is called damping ratio. So and so on, right? So let's get into today's class. This is lecture number 7. And today's date is 16/08/2021, right? So the lecture point is, today you're going to learn something called what is logarithmic decrement. So if you know the logarithmic decrement, you'll be able to estimate the damping in the vibratory system. That's why we have to learn this. And what is the energy dissipated in viscous damping. So these are the 2 points that we are going to importantly learn in today's class. And I'm going to start our class writing down the equations of the response of damped free vibration and its graphical representation. And we will proceed to this part of lecture. So in the last class, we had our response x of t. What was our governing equation, by the way? It is mx double dot plus cx dot plus kx equals 0. And this is second order ordinary homogeneous equation. And you have this is inertia force, and this is called damping force, and this is spring force. The dynamic equilibrium of its vibration is this all forces equal to 0, right? And this is what is the governing equation of damped free vibration. So why is it called a free vibration? Mathematically, how do you say that? If it is free vibration, you see the other side of the equation is 0. If I have here a forcing function, which is function of time, f of t, that can be another harmonic forcing function, then this is going to be forced vibration. We will see that in the next lecture. So the response of this damped free vibration, we had got it like this. What is that? E raised to minus zeta omega nt multiplied by C1 dash cos omega d. Look at the subscript here, omega d, here omega n, omega dt plus C2 dash sine omega dt. So this was the response that we had, and we know here omega d is defined as damped natural frequency, and that's given by 1 minus zeta square into omega n. So this is the relationship between omega n and omega d. And we can also write this response x of t in another form called x of t equals x naught e raised to minus zeta omega nt sine omega dt plus phi naught. Or I can represent this response by x e raised to minus zeta omega nt cos omega dt minus phi. So in this, we know that x naught is equal to x equals. So this would be given by, I'll write this, and how did you get, we did not do this derivation, but I leave it to you to do, similar to what we were doing for undamped free vibration. So this is going to be amplitude of vibration is going to be constant for both, whether it's x naught or x, same as given by, it's not constant, it's going to decrease. That's what in a vibratory system. But these two in these equations are same. So that is given by x naught squared omega n square plus x naught dot square plus 2x naught dot omega n into zeta divided by omega d square. This is all under the radical. And you would be able to write this phase angle omega d, of course you have written. Phase angle phi naught would be tan inverse of x naught omega d divided by x naught dot plus zeta omega n x naught. And phi would be tan inverse of x naught dot plus zeta omega n x naught by x naught omega d. And you know here we define C by Cc, which is the damping ratio. And you can also write C by 2m, that's equal to zeta omega n. And C by m is equal to C by m equals 2 times zeta m omega n. So these are some fundamentals, the relationship between damping coefficient, critical damping coefficient, and so on. Right? So critical damping coefficient value, C by Cc value is equal to 1. That's called a critically damped system. So that will not vibrate. There is no oscillation. That's called a periodic motion. If zeta value is greater than 1, then it is called the overdamped system. That is also aperiodic in nature. The damping value, least damping required, for its periodic motion is what is critically damped system. When it is more, then it is over damped system. So the shortest time period, time that it takes to comes back to mean position is what is given by critical damped system. We will see that in a while. Where these are all for an important case when zeta value is less than 1 and zeta value is not equal to 0. So when I say zeta equal to 0, this damped free vibration become undamped free vibration. You can see in this zeta, if I substitute 0, I would get this equation similar to what we were discussing in undamped free vibration. You can just do that as a homework and see. And you can see that how this x naught, x, these values are obtained. These values are nothing but obtained through the C1 dash and C2 dash values or phi naught or phi value estimated. Similar approach that we followed in the undamped free vibration, stating that its initial conditions. At t is equal to 0, what is my x naught, and t is equal to 0, what is my x naught dot. So if I have those equations, so if I differentiate this with respect to time and then have those two equations, I do the similar procedure, I can get these all. So these are your end results. So in this, if you substitute zeta 0, you see that what is that you are going to get amplitude the same as what we have got for an undamped system. If you put zeta 0 here, what you have is phi naught what you derive. So this is how you can remember these equations easily, right? One is to derive and know this. Another one is after deriving, remembering this while solving the problem. So this is what is in summary what we were doing in the last class.
Sir?
Yeah.
In the bottom right corner, C by M equals 2 zeta M.
Yeah,
1 M
2
is not
zeta
there.
omega n.
So M should be 1 only, right? C by M is already there, so M.
Yeah, 2 zeta omega.
Right.
Sorry. Yeah, correct. You're right. Very good. This is going to be just corrected.
And sir, what is written above it?
Yeah, just I'll rewrite it. So this is going to be, when I write C by M is equal to 2 zeta omega n. Why did I write this? I'll just say, is just write my mx double dot plus cx dot plus kx equals 0 is what is the governing equation. So if I divide this all by m, it is going to be x double dot plus c by m, x dot plus k by m, x is equal to 0. And I can rewrite this equation as x double dot plus c by m is what? 2 zeta omega n x dot plus k by m is what? Omega n square equals 0. So I can also write my governing equation in terms of zeta and omega n. So that this is my governing equation. So that is why I just have written this fundamentals, right? So you get from the governing equation, this equation form is because you understood these relationship, because you are knowing what is the definition of critical damping ratio, and you are able to have this all. So C by 2m is equal to zeta m omega n is because this term is there inside the radical of the roots of this equation that we have seen. So this is kind of always knowing this relationship. So do you get my point? Okay, if that is so, now let's look at another interesting thing that we have learned. What was state space representation of an undamped system, right? Undamped system, how does it going to look at today? So that's very simple, just to take a minute to understand. So what was our phase plane representation or state space representation? We have on x-axis the displacement and y-axis x dot of t, and here x of t. So if I take that, I represent this plane as phase plane. This is called the phase plane or state space plane, where you have displacement and its derivative on y-axis. So if that is so, we have seen that it is going to be a circle. It is going to be a circle for a undamped system, right? This was for undamped system. You remember we had this part in a previous lecture. Please look at it back again. So if that is so, I can represent now my damped system would be something like this. So I take a point, any point where I have my x of t and x dot of t here, right? So the amplitude here originally for this system, it was a here or a here. I can call that as x or x naught or x naught, whatever that amplitude we had got it for this. So now what would happen for a damped system is this amplitude would be decreasing exponentially, and that could be represented something like this. That would be represented something like this in a cycle. So this is one circle represent 2 pi, one cycle. So the amplitude, what was there at A, it's reducing and it is going to be 0 at a point of time when it is a damped system, and that damped system also under damped system. So only under damped system can have periodic motion. The motion is oscillation, correct? Whereas you also have an over damped system and a critically damped system. So what is critically damped system? When zeta value is equal to 1, that's called the critically damped system. So I leave it to you to put the zeta value 1 and then see what are those equations and all. That can be a kind of homework for you looking at these two cases, but I just represent how is it going to be in this case. So this critically damped system is not a periodic motion. That is not representing oscillatory motion in your system. That is an aperiodic motion. An aperiodic motion also at the quickest time it would be reaching to this 0 amplitude. So you see that would be represented something like this. So this path. So if this is the amplitude time, you see it would reach the time quickly. So this is what is called a critically damped system. And over damped system, if you look at, that is also aperiodic. It would take some long time to come back. So that would be somewhat, it will come like this and go. So this is the over damped system. Over damped system. And it takes longer time. So this is sluggish, more sluggish. So if initial displacement is given and then you leave it, it will come to mean position taking longer duration. Whereas if the system is critically damped, what will happen? You disturb the initial condition, initial position of the mass from its static equilibrium position. What will happen? That will quickly come back to its static equilibrium position. Rather, it will go further. That means it will come back and the system will be aperiodic. It will not. So this is an important design requirement in many of the system, particularly in big gun barrels. So the gun barrels, when it is to be shot, so you see that there is recoiling mechanism, something is there. The recoiling mechanism should be such that should not create any pressure on the shoulder of the army man. At the same time, it has to quickly happen. So for that, the damping present in the spring damper and then recoiling mechanism would be critically damped, so that when it's fired, then there will be vibration. It won't be vibrating. The barrel will come back quickly to its mean position, and again next load of gun will be happening. And there, if you have over damped system, what will happen? There will be phase lag. It will take some time. Then next recalling, you have to wait and so on. So over damped system may not be suitable in such case. So you have a damping coefficient in your system, such that C by CC ratio zeta greater than 1. It is not preferred. It is not vibratory system at all. It is hardly some of the application based requirement. But if we are seeing it C by CC value 1, that is mainly in such kind of system. The dash part has to make your oscillation arrested, aperiodic. So the disturbance because of firing of gun should come back, the barrel should come back to its mean position quickly. So that's what is the critical damped system. And damped system is something which is going to take some time and then it will die out. It will die out at some amplitude in this variation. This kind of Archimedean spiral appearing, so it is going to be varying. So this plot is what variation of your velocity of harmonic motion as function of the displacement. And this diagram is what is called a phasor diagram or state space diagram. Right. So this is what another comprehensive understanding of these types of vibration. And then let's now look at the response. How does it appear for all these four cases, right? So that's very interesting again. Let me just to plot that. Instead of plotting, I will just to show you the plot. How does it appear? And we'll quickly able to understand it. So that's going to be something like this. So look at here now. What is that I have? This is that combination of all the cases, what we have been so far learning. So look at first the kind of damped system. So damped system is under damped system. Zeta value is less than 1, where you have omega d is smaller than omega n. When zeta value is 0, that is undamped system. So when you have this undamped system, you see this amplitude is constant. And the time period of oscillation is given from here to here. So this is time scale. So this time interval for completing one cycle. So from this point to the next corresponding point in a cycle, or if you can say this point to this point, like that you can take, and that is given by this in a free vibration where it is 2 pi by omega n we have seen. Whereas in damped vibration, what is happening because of damping this omega d? What is omega d? Is under root of 1 minus zeta squared into omega n. So since the omega d is present, you'll have omega d smaller than that. So when smaller frequency is there, you'll have the wavelength of that small. So you see, this is what is the dotted one represent under damped system. And you see this amplitude here, what we had at the first cycle, right? So this is x1, and this is going to be x2, and this is going to be x3. So like that, it is going to be 0 at one of the cycle, right? The amplitude x1, x2, x3 is decaying, and the decay, if you look at, that would be exponentially decaying, like this it will go. And you look at here, critically damped system, zeta equals 1. You see this is, there is no overshoot like in this case, just to falls to this 0 amplitude quickly possible, and that is it is critically damped. Over damped system, when you take, look at this dotted line, it takes a long time and then it will be ending. But there's no oscillation in these two cases. That is why these two, over damped system and damped system, are aperiodic. So what are these parts? These parts are our response x of t. So we had x of t under undamped system, and we also had and looked at today's morning class, starting with x of t for under damped system. So that is that. So to this, we can go ahead understanding two important property called the logarithmic decrement and energy dissipation in the system. And that's what is the objective of today's class. So let me just give you again the response of today's class, and then start with the understanding of that. So let's look at now this response. This response. Look at now this response. So this is response our harmonic motion. So what is the response that we had here? This x of t is what is equal to here is to minus zeta omega n t within bracket c1 dash cos omega dt minus cos omega dt plus c2 sin omega dt, or this will be zeta omega nt cos omega dt minus phi And you have, of course, here amplitude x. And that would be also represented by x naught e raised to minus eta omega nt sine omega dt plus 5 naught.
Sir,
So these
I cannot
all can be three
So
forms.
I cannot
Yeah.
see what's on the
see
board,
the
sir.
board is not visible.
Yeah, nothing to worry. Later on, you can watch the video, right? You cannot see what is there on the board. I don't understand, but I'm able to see here. Maybe your place there. Be patient.
Sir, we can't see.
Sir,
Voice
even
is
me, sir.
cracking, sir.
Yes, sir.
Check. What about? Are you able to hear me now? Are you able to hear me now? I'm able to hear and respond. Are you not able to hear me?
Yes, sir.
So
Yes,
we
sir.
are able to, but it's cracking, sir. Your voice is cracking.
Okay. See, those are not able to listen. There can be a reason that at your place you may not have a network issue. Nothing to worry. This video lecture is recorded. Please be patient. Later on, you can watch. Right? Ashmita, you can do that later. So let me continue with that because I am running short of time. In case it is not clear in the video that I observe, I will clarify that once again. Nothing to worry, right? So I hope you are able to see that shared screen. In case it is not appearing for you, that would be because of your end network issue. Please be patient. So this is the response here that you get. Look at here, this amplitude here is decaying. The decaying is what is happening exponentially, and this part would be taken care by this x e raised to minus I omega nt. That's what is this. So exponentially decaying. Then it is unstable system, then exponentially increasing function. That's the possibility in hybrid, in the mathematical representation of vibration equation. We will not see that at the moment. And you see here, what is important is how the time period of oscillation, damped oscillation is defined. That is from any point, if I take x1 of t response, I'll go for a corresponding cycle completion, similar point, and that is my second amplitude. So this amplitude would be equal in case of undamped system, but here it is decaying. So this decay is what is going to help us to define what is called a logarithmic decrement. Logarithmic decrement. And denoted by delta. What is it? How does it been defined? It is defined as a natural logarithm of the amplitude ratio, right? Natural logarithm of log base e of its amplitude, successive amplitude x1 by x2. So if you look at here, this x1, x2 are an arbitrary at time t1 and at time t2. I look at this, that one cycle, and the amplitude ratio of these two is what is going to give me, or the displacement of these time instant t1 and t2, which is deciding my time period of oscillation, is what is going to give me this logarithmic increment value. So it is defined as a ratio of displacement, natural logarithm of ratio of displacements x1 and x2 in a cycle of operation two time respectively. If you understand that, I can just that here in this fashion, right? So how can I input that now? Logarithm, natural logarithm of anything base this going to be simply the amplitude ratio, right? Yeah. That's going to be, I'm going to substitute this now in this. So it's log base e. Within that, x1 of t is what if I take this is x1 of t will be, I'll take now here this cosine function, and it is going to be x e raised to minus zeta omega nt cos omega dt 1. So this is going to be T1 minus 5 divided by, and here it's going to be x raised to minus zeta omega n T2. So this is T1 and this is T2 cos omega d T2 minus 5. Right? So I just substitute what is x1 of t and x2 of t. x1 of t is at t is equal to t1. x2 of t is at t is equal to t1. So I just use this form and then I have just to put it here. And you see here, interestingly, now what is this omega d t2? Omega d t2. So omega d t2 I can rewrite this as omega d. T2 is this time, and that is t1 plus the time acceleration. So I can replace that as t1 plus tau d. So that's going to be omega d into t1 plus tau d is 2 pi by omega d. So this is going to be omega d into t1 plus 2 pi by omega d. And this goes out, it's going to be t1 plus 2 pi. T1 plus 2 pi. So, why do I do that? As you know, cosine function now. Again, repeat after cycle 2 pi, it will have the same value. So, just look at now. This is going to be, if I substitute in this term, what is that in cos term? So, cos omega d t minus 5 would be same as cos. Now, this omega d t is replaced by this is t1. And that is going to be same as cos omega d t1 plus 2 pi minus 5. So that's going to be same. So that's going to be same. If that is so, I would have here this term is going to be replaced by this. The cosine term goes in numerator and denominator, and will be left with my logarithmic decrement is natural log of x1 by x2, and that would be equal to natural log of x2 minus zeta omega n t1 by e raised to minus zeta omega n. This t1 is going to be t1 plus td, tau d. So this is going to give me now further. I have numerator and denominator. This goes inside, so that minus goes up. So I'm going to have this natural log of e raised to zeta omega is what is my logarithmic decrement. And you see, it is natural log of exponential function. So log of exponential power will be this is simply going to be simply zeta omega. This is omega n, omega n into tau d is what is my delta. So I could define now my logarithmic decrement like this, and that's going to be zeta omega n. This is 2 pi by omega d.
Excuse me, sir.
Yeah.
None of us can see anything, sir. It's black screen or it's pause for someone.
I will repeat the lecture later on. Let me finish this, right? In case so. Because see, I can't stop and no, my thought process don't disturb. Okay, I understand. This is all the difficulty of on classes. In case you are not able to see, what can I do now? I don't want to stop. Let me just complete my flow. If I see back my video that's blank and you are not able to view, I would repeat this lecture and post it again. Okay, that's what I can help you out. Is that
Okay, sir.
yeah? Good. So this is what is delta equals the This is omega d. It's not omega delta, omega d, right? So this can be further simplified like this now. 2 pi zeta omega n by omega d I will substitute. So the zeta omega n 2 pi divided by omega d is what? 1 minus zeta square. 1 minus zeta square radical into omega n. So this omega n goes, it's going to be 2 pi zeta by 1 minus zeta square under root. Is what is delta. So logarithmic decrement is explained now as the 2 pi zeta by root of 1 minus zeta square. So the zeta value can be very small for lightly damped structures. For example, you see metal structures, steel structures, the damping value is very less compared to that of rubber structure or tire. Tire damping will be more compared to that of lightly damped. Other steel plate will be very lightly damped. That's why if you just tap it, it will vibrate for a long time. Whereas if you tap on a tire, vibration is invisible. Suddenly it goes up. So that is what is the difference between the damping value. So the damping value is very less in the system. That's called a lightly damped structure. For the lightly damped structure, you can consider zeta value is very less than 1. In such cases, you can approximate this is going to be simply 2 pi into zeta. And just to multiply zeta by this, I would get that present in the system is approximately equal to delta. So why do I write it now like this? What is delta is logarithmic decrement. Experimentally, I can find out the reduction in or the ratio of amplitudes of consecutive cycles. So, or I can find n number of cycles. So from one T1 to T2, if I have m number of cycles, I can take that. What is the amplitude at first cycle till nth cycle? So I can find out experimentally what is this logarithmic decrement value, so that I would be able to find out what is the damping ratio in my system. That helps me to quantify the damping of the system, right? So that's where I will see this. If I have to go back without considering structure, what would be the way I would be able to find out experimentally? Then I should take this as it is. The delta is going to be 2 pi zeta by under root of 1 minus zeta square. So let me rearrange this term square on both sides. That's going to be delta square. That's going to be 4 pi square zeta square by 1 minus zeta square. So cross multiplying and then rearranging the term, writing it for zeta, that would come as zeta equals delta by under root of 2 pi whole square plus delta square. So this is going to be like that. So if I know now this delta from for the vibratory system, experimentally I will be able to find what is the damping ratio of my vibratory system. And now let's look at if it is of M cycle, how do we generalize this definition of logarithmic decrement? So if I have my amplitude ratio of x1 to x2 is xm plus 1. So mth cycle this ratio can be expressed as x1 by x2, x2 by x3, x3 by x4, and so on. It's in multiplication, it's going to be xm by xm plus 1. So mth and m plus 1th amplitude in a cycle. So this product is what is going to give me this. I know x1 by x2 is what is now defined logarithmic. Just now we have seen. So it's going to be like this. So any jth amplitude ratio like that, if I take, I can rewrite that in this way. So natural log of xj by xj plus 1, jth successive amplitude ratio. So jth one and next one, if I take, that would be given by ln e raised to zeta omega n into tau d, right? So that's what we are defined now. It's x1 by x2, then this is what we define. So by substituting this now in this above case, I would have now this for m cycle. So this is going to be ln. This is going to give me ln xm by xm plus 1 can be equal to ln e raised to zeta omega n m times tau d, m cycles. So it's going to be delta equals zeta omega n m tau d. And this m will be brought down. Right. 1 by m delta is equal to, see, before this you write this, delta is equal to before this. So this whatever there, that is brought down as 1 by m, and I'll rewrite this again into ln this xm by xm plus 1. That's going to be 1 by m ln raised to e raised to zeta omega n tau d. So this is nothing but your expression e raised to that. So it's going to be 1 by m. 1 by m. Not 1 by m. If it is x1 by, if it is ln, x1 by ln x1 by xm plus 1, then it is going to be this m tau m zeta into omega n tau d, right? That's what is delta. That's not the equal delta. That's this ratio. If this is the ratio, I can rewrite this as this 1 m is brought down. 1 by m is brought down. ln x1 by xm plus 1. What is zeta omega n tau d, which is my logarithmic decrement delta. So delta would be, if I have n cycles measured, I have to divide the ratio of first amplitude to nth amplitude logarithmic ratio. That should be divided by m. That's how we get this is. So this is 1 by m ln first amplitude, not the successive amplitude. After m cycle, what is amplitude if we have? That's possible in the experiment to get. Then your natural logarithmic decrement would be defined in this case. So this is how you define what is called a logarithmic decrement. So it's connected network is there. So are you able to see now? Is it visible or still not visible?
No, sir, we can't see anything
Not
at all.
visible.
I
So
don't know. Is it
actually,
for
the screen is freezed.
Yes, sir.
Screen is freezed.
Some of us are just seeing a black screen, while the others we are seeing your screen is frozen. Like for me, your screen is completely frozen.
I don't know what's happening, but I do not have any warning here that it is
So you
Sir,
can just
your network is
unshare and reshare it
we can't
again.
hear you, sir. Your
Yes, sir,
network
we
is actually
can't follow from where you're taking the equation, where you're substituting it, where you're writing it.
yes, sir. Your network
Yeah.
is slow. Your voice is breaking as well.
Oh, my network is not good.
Yes, sir.
Then only it can happen.
Yes, sir. Your network is not good, and we can hear you properly. Like your voice is breaking at times.
Okay, okay. Okay. Anyhow, then let me stop at this point and start going for further. And let me check if it is not proper. I would maybe extra lecture I will take. I will put this PPT or matter, or I will record once again my lecture and send it. That because if it is not here still, I think there's no need of continuing at this point. So it's about to finish now. I thought of starting with the damping dissipation, energy dissipation in a cycle of vibration. I will do that later. So let me stop at this point. And if you have any doubt, okay, you're able to listen me at least, right?
No, so the voice also is breaking.
Voice also is breaking. That anyhow, I'll stop at this point of time. Lecture. And we will meet again in the next class. I would count the attendance for voting. Attendance. But for all